chances of having some common factors, and again there will be some more possibility to make it in the simplest form. So make the group as minimum as possible so that it is mainly the group will be in larger size. So that is why that is what we learned in the last class. So in addition to what we discussed, there is one more condition called as don't care conditions in the K-map. So as you could see in the last class, we were drawing some K-map. And for example, if it is like this kind of a K-map with possibly, if it is 3 variables and we had 8, so maybe my A is here and the BC is here or something like this. So we had here. So we were just plotting from the truth table itself. We just see if this is 0 and this is 1, and this should be 0, 0. This should be 0, 1. This should be 1, 1, and this should be 1, 0. So if this is the K-map, what we discussed earlier, and we have a truth table where the places is like, for the places of 0, 0, 1, we have a 1. And for the place of 1, 1, 1, we have a 1. And for 1, 0, 1, 1. So only this we have. But there may be chances when the circuit will tell, actually, we don't care that condition. Earlier, even we discussed like this, right? Just a moment. So given a condition here, we discussed and we were able to draw some truth table from here. And maybe, for instances, there may be chances we don't know what will be the actual output. I mean, they don't tell you what happens when there is a specific output like that. So in that condition, you are allowed to use an X, which is called as don't care condition. For example, the meaning of this X is this can be 0 or 1. No problem. Depending on certain factor, this can be 0 or 1. And that particular X format is called as don't care condition. So what is the advantage we have with this don't care condition is maybe from your truth table, you found out that for the values 0, 0, 0 and for the value 0, 1, 1, we have a don't care condition. And for the value 0, 0, 1 and 1, 0, 1 and 1, 1, 1, we have an on condition. And this, all the others will be, you could see this will be 0. This also will be 0. This also will be 0 or something like this. This is your K-map. Now, just imagine if this don't care condition is not available there. If this don't care condition is not available there, we will have a chance of making a group like this. And we will have a chance of making a group like this. Okay. So this is the basic way how we would have made any group. And for this one, we have a Boolean expression, and this one we have a Boolean expression, and together we will write up our Boolean equation. But imagine from the truth table, you also found that there are 2 places with a don't care condition. So the best part of having a don't care condition is this will allow you to make a group like this. So listen very carefully. You are able to make a group. For example, earlier there was a chance of only making a group like this and group like this. But since if there is a don't care condition, you are getting a chance of making a group of 4, right? So if you get that opportunity, you have to make use of that and make a larger group as possible. Because this don't care condition means this X can be, the meaning of this is X can be equal to 0, or at certain places, X can be equal to 1 also. So we define this condition as a don't care condition. So imagine if there was a 1 here, we are able to make a group of 4 now. So using that benefit, we just make a group of 4 and try to write the Boolean equation here. And if this don't care condition was not there already, we will have 2 groups. And one more condition you have to focus is don't try to make a separate group to include a don't care condition, but you can make use of it. For example, if this is needed, you can use it. But don't try to create a new group for including this don't care condition. It is a don't care, which means if you need, you can use it. But don't create groups, new groups to include all the don't care condition. So that is the logic behind this don't care conditions in a K-map. I repeat again, if there is a don't care condition, what you have to do is simply, if that person can be utilized to make a large group, use that person. Or if that person is there idle here, maybe even this case, this don't care is not there maybe, and you have a don't care condition here, but we don't have any use. See, now I just delete this orange box. Now I have a don't care condition here. From the truth table, we have a don't care condition there, and maybe we have only 0 here. Now see, if you want to make a large group, we are just trying to use this, but it is of no use. Simply, you don't need to make a group to include this. Why? Already all the ones are included in 2 groups. So this is enough. You don't need to create a new group to include the don't care condition. But again, if it was here, maybe here, this will help you to make a group of 4 no? That time you can use that condition. So that is the logic behind a don't care condition. Is that clear? Is that clear?
Yes, ma'am.
How about others? Is that clear?
Yes, ma'am.
Okay, now maybe I can open up an Excel sheet for you and give you a small question. You can try. So maybe if we are here, maybe with a don't care condition, right? You can just see like we have A, B, C. So you have 3 input variables A, B, and C. What's that?
We couldn't see the Excel sheet.
You can't see the Excel sheet. Let me share it again. Can you confirm whether you see my Excel sheet?
Yes, that's fine.
Okay, now we are here with this one. So these are my inputs A, B, and C. And this is my output, right? So if you have 3 variables, how many possibilities are there?
8.
8. So
8 input.
Okay, 8. Now we are going to make it here. And your output is also given here. So this is your variables. Now I'm going to just repeat this. So in this condition, it is going to be 0, 0, 1, 1. So this is going to be 0, 1, 0, 1. So now our truth table is almost there. Now we have to find out like what would be our potential output for this. So given, rather it can be given as a sentence type, or else they are just going to tell you what are the values it is going to have, right? So imagine they have given you only when all the inputs are 1 and all the inputs are either 1 or 0, you're going to get a 1. In addition, whenever there is more number of 1, you're going to give maybe like this. Just think this is the circuit we have, right? And for certain conditions, they are not giving you what would be the output. Maybe here it is 0. Maybe here it is X. And maybe here this is 0. Now, you know, for drawing our K-map. So if this is our K-map, if this could be our K-map, right? And you have 2 things here. So this is going to be your A and this is going to be a BC or something. So I'll just put up here 0, 0, wait, 0, 0, 0, 1, 1, 1, 1, 0. And this will be your 0 and this will be your 1. So these are your factors maybe. So in my instance, I'm going to use right? This is going to be my A and these are my BC, right? These are my BC. This is B and C. So that's it. Now what you have to do is right. So you have these values. So you're going to right. So you have a K-map like this also, right? So now from here, you have to just transfer them to this K-map. So if it is 0, 0, 0, what is the one you're going to have? If it is 0, 0, 0?
A bar, B bar, C bar.
No, I'm telling you here. Yeah, here. 0, 0, 0 mean you have an output of 1. If it is 0, 0, 1, you have an output of 0. If it is 0, 1, 0, 0, 1, 0, you have an output of don't care condition. For other one, 0, 1, 1. So 0, 1, 1, you have an output of 1. Then here you have 1, 0, 0. This is going to be 0. Just a moment. Right? So you have this 0. Then if it is 1, 0, 1, 1, 0, 1, it is going to be 1. Then if it is 1, 1, 0, 1, 1, 0, it is going to be x. 1, 1, 0, it is going to be x. Just a moment. So again, you have, if it is 1, 1, 1, it is going to be 1, right? So that's what we have here. Right. So now your K-map is done. Right? Now, how are you going to make your groups now? Just try. With the only ones, you have to make a group, right? So just check how you can make a group. Try.
0, 1, 0, that corner.
See, for example, if you have here, this case, right? If you have here, you make a group of 2. If this don't care condition was not there, you can simply make a group of 2. But with the don't care condition, see, you can make a group of 4. It's possible, right?
Yes.
Yes. Then here, for this person, what is the thing you can use?
It's for 2.
It's a group of 2. And for this one,
That's,
what is possible?
Horizontal x and 1.
Yeah, you have to wrap up like this, right?
Yes.
So you have a group of 3, but still you have minimum number of factors. Now we will just find out maybe for just check your red one. If you check your red one, oh wait, if you check your red one, right, if you check your red values, simply just look at what are the values that is not changing, right? Since it is across all these things, both A bar and A is changing. Among these two, what happens?
B.
B is not changing, C is changing. So you have to label this as B. Now going back to the next group, which is in green color. So you can have a look that it is A bar, right? This is A bar. This is also A bar. So for the green group, you have A
bar.
Then you have to check the B component that is changing. And for the C component, that is not changing, and this will be C bar. Why is it C bar? The value that is not changing is 0, not 1. So we have it like A bar, C bar. Then again, going back to the next group, the blue one. So if you can have a look at this blue group. So this blue group, you can see
C.
the value, this A value is not changing and it is 1. So you put A.
C.
And here in these two, B is changing, C is not changing, but the value is also 1. So it is
Yes.
going to be AC. So together, if you have to put up these equations together, you can write it as a sum of product, like AC plus B plus A bar, C bar. Is that okay?
Excuse me, miss.
Yes.
For the green one, we have the A bar.
Where?
The green one.
Yeah. Yeah, why? What's the problem?
That's a bar and B also including, right? A bar, B, C bar.
Why B here is 0, B here is 1, no?
Ah, okay.
C
Okay.
only not changing.
Okay, A bar, C bar. Okay, that's
Yeah, A bar, C bar.
okay.
How did the output come? I didn't get your question, but simply output is how you have to make a group. After that, they are called as Boolean equation, like a Boolean expression. You will have like 3 groups mean 3 equations will come. So simply, if you consider the group like this, you have to follow up the values which are not changing across the group. Only that will available at the final answer. So if you take this red group, simply you can see the value, this one. So maybe for better understanding, I can also put like this way. So just consider this red group, okay? Red groups, what are the red groups value? What are the values under the red group? 0, 1, 1. 0, 1, 1. What is this value?
1, 1, 1.
0, 1, 0. What is next value here?
1, 1,
1, 1, 1. What is the next value? 1, 1, 0. The red group components, these are the 4 people, right? So you have to only list down the person which is not changing across the group in the final answer, right? So simply, if you consider all these groups, see, this is the value for A, which is not constant. It is changing from 0 and 1. So you don't take it. Take the value of C. That is also changing 1, 0, 1, 0. You can't take. But check the value of B. Is it changing? The value of B is not changing. That is why in the final answer, you have only this B. Likewise, similarly, you can do for the other group also, maybe for the blue group here. So the blue group has only 2 components. The first component is this one. This person is 101. Next person, this person is 111. So just check what are the values that is not changing from here for the blue group. So you can simply track them. This value is not changing and this value is also not changing, but the middle B value is changing. Since both are 1, the value that is not changing is 1. I put A here and C here. In this case, the value that is not changing is 1. That is why we have put a B. Similarly, do for the green, light green group also. The values are 0, 0, 0 and 0, 1, 0. So which is not changing? A and C. And what are the values? 0. That is why we put A bar, C bar. Is that okay? The one who sent me in the chat box. Is that okay now? 23 ICT 76. Is that okay now? Okay. So this is how you do this. Now again, So that is one of the use of having a don't care condition. So still you can do all these things. So I'll give you some time. You can try this, but before that, I will just teach you what is this, right? Just like a Boolean equation, these Boolean equations can be written as a kind of a Boolean functions also. So Boolean functions mean simply, I will read out what is this. You have a function called as A, B, C, D. The meaning is it has 4 input variables and the variables names are A, B, C, and D. If you have 4 variables, just a moment. Right? If you have 4 variables, how many possible combinations are there?
16.
16. So 16 combinations mean you are just telling here sigma, sum of products mean you are telling the value at 0, 1, 2, 4, 5, 8, 9, 10, 11 are going to be 1. Other values like 3, 6, 7, 12, 13, 14, all these are
0.
right? So 0. So in this way, you can transfer this Boolean function into a truth table and straightly from the truth table, you can build up a K-map. If you are not comfortable with directly transferring them from this equation to K-map, in the middle, you can plot up a truth table and from the truth table, you can go to a K-map. Okay. So we will try this one and other one you have to try here on your own. So this is my equation. So let me open up the Excel sheet. So you can see this is the equation we have, right? The equation here is f of a, b, c, d, which is sigma of 0, 1, 2, 4, 5, 8, 11. So this is going to be a group of 16. So this is my K-map, all right? So just look at your K-map. It is going to be like this. So I have all these values, right? You have all these values. So here I'm going to consider A, B, and this side I'm going to consider C, D. This one very careful, okay? Most of them make mistake here only. You don't understand which is what. So this is going to be your AB. This is going to be your AB. And this is going to be your CD. Right? So I'll first teach you how to directly map it. So this is AB and CD. I will also put up the values. So this is going to be 0, 0, 0, 0, 0, 1, 1, 1, 1, 0. Same thing here, 0, 0. This is going to be 0, 1. This is going to be 1, 0. Sorry, 1, 1. And this is going to be 1,
0.
0. Just a moment. Right? So these are the values. So straightly from here, you can map. So if it is 0, 0, 0, 0, I will even write up something. You can check if you can follow me. This is 0. This is 1. This is 3. And this is
2.
2. Right? And this is going to be
4.
4. This is going to be 7. And this is 0, 1, 0, 1 mean
5.
And this is 0, 1, 1, 0, so 6. Likewise here, this is going 1, 1, 0, 0. It is going to be 12.
14.
This is 12. Okay. And this is 1, 1, 0, 1 mean 13.
14.
This is 15.
15. 14.
And if it is 1, 1, 1, 0, it's going to be 14. And this value is 1, 0, 0 mean it's going to be 8. And 1, 0, 0, 1 mean 9. If this is 1, 0, 1, 1 mean 11, right? So this is going to be 10.
10.
Just try to understand, if you can understand this, how these values are coming. Simply, if it is 0, 0, 0, 0, first AB, then CD. So 0, 0, 0, 0 mean value is 0. If it is 0, 1, 1, 1 mean value is 7. Likewise, you just try to map them. If you are not able to directly map it from the equation to your K-map, no problem. You can even build up your truth table and plot these values. So it will be like this. Maybe you have A, B, C, D, and this is going to be your output. So here, this is going to be 0, 0, 0, 0. And again, this is going to be 1, 1, 1. Right? Just look at the truth table, how this is working. So again, this is 4 times. This is 4 times. This is going to be 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1. Then here it is going to be 0, 1, 0, 1. Right? So this is how your truth table is going to be if you're supposed to map it from here. Right? So here you can see, zoom, I have to zoom. Okay, wait. Right. So here you can look it as a truth table. If you check this, so they are telling you this value is 0, 1, 2. Just for easy, I'm mapping these values also. So how many values will come? Up to 15. Right? Up to 15. You have different values. So now from the Boolean function, simply you have to put the values 1 and 0. So what is, it is showing as a sum of product at 0. This is 1. At 1, it is 1. After that at 2, it is 1. After that at 4, it is 1. At 5, it is 1. Then 8, it is 1. 9, it is 1. 10 and 11. The other things are 0, or sometimes even if it is a don't care, that also will be given. But now they have not mentioned whether it is don't care, so we give it as 0. Right? So this is your stop. You can have a look. Now, what you have to do is, for these values, you need to mark a 1 in the K-map. So how to do is simply right? Just a moment. Right? So if it is here, simply the places where you have 0, 0, 0, 0, you just mark. From the truth table, you know to plot a K-map, no? You know to plot a K-map now, so directly from there you can do. If not, from here itself you can do. So from here, you're going to simply find where is 0. So 0, 1. After that, 1 also 1. Then 2, it's here, 1. 4 also 1. 5, 1. 8, 9, 10, 11. So these are the places you have this one. Now, simple. Now you have found the way. You have to make it as a group. So how to make it as a group? Maybe you can have a look. This can be made as a group of 4. Again, another color. Maybe this can be also made as a group of 4.
4.
Only that is possible. And for this person, what to do?
2.
This can be made as a group of
2. Vertically horizontal.
Group of how many? It
It's a
can
4.
be
I
made as a
think
group
the
of 4 again, because you
yes,
can take a group here.
corner.
All the corners you have a 1. So you can make it as a group of 4. I always tell you, if it is a larger group possible, always go for the larger groups. Okay. So in this instance, how are you going to find out is, now for easy, I will just clear these values. Wait. Right. So I think one of the one also deleted, no? Was it here? And here, no? Okay. Now we are going to make it as a group of 4 for this. And we also can make a group of 4 with this. And again, you can make a group of 4 like this. So for orange, you can just check 0 not changing, right? 0 is not changing. And here 0 is also not changing for C. So what is the one? A bar,
Bar and
C bar,
C bar.
C bar. Now take the other one. Maybe the green group, you can see, since it is in the same line, this 1 0 will not change for all the values, because this is 1 0 0 0, 1 0 0 1, 1 0 1 1, 1 0 1 0. So this is not going to change, right? So that is going to be 1 0. So it is A,
B bar.
B bar. A, B bar. After that, you can check this is moving through this line. So all the values are changing. So it is only A, B bar. And again, you're going to check the other one, which is our magenta group. You can see if you're not comfortable to check all these 4 corners, just write up the value as I told before. Maybe this line. So maybe here, just check this line. It is going to be 1 0 0 0. For this one, you can, if you are comfortable, straightly from the graph, you can find. If not, you can just make like this also. This one is 0 0. Now for this one, the value is 0 0 1 0. Then for this one, the value is 1 0 1 0. Just carefully check all the values, right? For the magenta group, check the values. A, is it changing?
Yes.
Yeah. So you don't take that. B, is it changing?
No.
No. And what is the value? It's
B
0.
bar.
So it is going to be B bar's value. C,
Changing. D bar.
this. Now you are going to check this one. C, changing. So you can't consider that. D,
D bar. Yes.
D is also not changing. All are Z. All are 0. So
Yes.
Since it is all 0, it is going to be B
D.
bar, D bar. Is that clear, everyone? Is that clear, everyone?
Yes, miss.
Yeah, so there is one more question I will let you do. Please tell me only the final answer, okay? Sorry, I will give you some time. Try to do and tell me the final answer. So I will open up the PDF for you with a question. These two, try both. And whenever the equation is given like this, in these places, yeah, I have to cut off one. Wait. This is not there. This is just 0, 4, 5, 7, right? And in these places, if it is given like this, the meaning is sigma D mean it is the don't care condition. So in the places 3 and 15, try to put a don't care and try these two questions. After that, we are done. We can move to the other section. Try this. I'll give you some time. Anyone?
Yes, miss.
So I think now, what was the equation for this?
B bar C
Just a moment. So you have B bar C,
plus BC bar
BC bar,
plus A bar B bar.
A bar, B bar. Others, did you get any different answers? Others? Did you get any different answer? Or did you get this answer? Others? Why don't you respond? How about others? All are tired today? No response? So for this one,
That one is AB
okay,
plus AD
AD plus,
plus BD
okay,
plus A bar C bar D bar.
A bar, C bar.
C bar D bar.
Okay, I think I have got an answer from one of your friend.
That's
can-
a A bar, miss. A bar C bar D bar. So the last one.
A bar.
Last
Last.
one?
A bar C bar D bar.
A bar, this one, no?
Yes, A bar C bar D bar.
This one?
Yes.
Okay, so your friend has given me an answer. Others also you can try. So just check if you are able to do this, right? So it is here. With this, the Boolean logic is over. I will upload the slides also. So you can check from there. So with this, the logic part is almost over. So as I told you, there are two components of this particular subject, that is logic designing and computer organization. So far we have been learning about logic designing. The rest of the part is computer organization part. So that is almost everything is theory with only few maybe mathematics stuff, not much, right? So with this, we conclude this series of logic designing and we move to the other one. So just a moment. Our internal Viva is ongoing. I have to join as a examiner. So I will just start up this session and we will continue in the next class. Okay. So this is basic components in organization of computer, lesson 4. Right. So now you can see the learning outcome of this is you have to mainly understand what is computer organization and what is computer architecture. These two are two different terms and you have to identify, you should understand the difference between them. What is an organization and what is an architecture? In addition, you also should know what are the basic components of any computer, what are the basic components of CPU kind of stuff. So these are the learning outcome of this particular unit, right? So moving on to this. So I told you there are two terms here. One is called as computer organization. The other is called as computer architecture. Although both appear to be a same term, computer organization and computer architecture, both are indeed different. Both have a different meaning. So as you can read from the slides here, right? As you can see from the slides here, architecture means actually how should be a computer there, what is the structure should be there is defined by the computer architecture. Simply the abstract, the logical aspects of the system are given through computer architecture. In addition, if you know the architecture of any computer, they will be given how you organize them, how you implement them. Those details are called as computer organization. So be clear, there are two terms. One is computer organization, the other is a computer architecture. Architecture mean it is simply like a blueprint. For example, if you are telling a car, you know what a car should be, right? There should be an engine. There should be, maybe if it is a car, a four-wheeler, you should have four wheels which are connected. And there should be a way to have a fuel, right? Maybe diesel or the petrol or whatever. And there should be a steering to control the tire. Then there should be an accelerator, brake. Likewise, you know how a car should be. Similarly, how a computer should be is given by a computer architecture, right? How it should be. How should be the design? How should be the structure? It is called as the computer architecture detail. So if it is a computer, if you want to tell something as a computer, it is simply, it should have a input device. It should have an output device. There should be someone to process the information, and there should be some way to store the information. So likewise, you are telling the fact how a computer should be. That is computer architecture. In addition, if it is a computer organization mean, what are the parts you are going to use? For example, if it is an input device, how are you going to connect? Like, for example, how keyboard should be there, how mouse should be there, how the CPU size should be there, how the processor should be there. Likewise, you are telling all the implementation detail. They are called as computer organization. So we are moving further. These are the two ways how we can classify the organization and the architecture. The instruction set architecture, what is the number of bits that is used to represent various data type? Maybe when you buy a computer and this one, you will just tell whether it is supporting 32-bit operating system or 64-bit operating system. You have a question. So those things are called as architectural attributes. And if you have some details like what is the RAM, what is the bus, what is the ALU, certain stuff, what are the parts you are going to connect, and how the data is flowing, all those details are called as organizational attributes. So simply, you must be able to understand the difference between the architecture and the organization. Architecture means what the system actually do, what it should do. And the organization lets you know how that particular system is doing that. Okay. And it is a very high level detail. It is only conceptual. We don't know the actual fact, but this gives you the implementation detail, the organization. And this one, it is mainly focusing on the instruction set. What are the data types we use? Everything is from here. And if it is computer organization, it is given what are the circuit type, what signal should go, everything detail is given through a organization. And even simply it is considered as a blueprint of a building. And simply this is how the actual things are done. Even the plumbing or the wiring or the structure, the building, everything is given by the organization. This is the implementation detail. This is only the conceptual detail, how it should appear. So that is the basic difference between the two. So in short, we think that architecture is like deciding how a car should perform, like whether the speed or the fuel efficiency or whatever. And the organization will tell you how the engine should work, transmission, what is the type of system, fuel system you're going to use, everything is given by here. So one thought for you is simply almost all the computers will have similar architecture, but the implementation detail, the organization will differ. So you can take a MacBook and a Dell laptop. Both have keyboard as an input device, everything same. They have a touchpad input device, it's the same. It has a processor, everything the same. But see, the way of arranging them is different with a MacBook and a laptop from any Windows OS laptop or something like Dell or whatever. See, that is how even not only the Dell, like even if you take another one like HP, that organization also will be different. Maybe it gives a touch screen display. So it, for example, that is why I say all the computer architecture is same, but the organization differs for certain computers, right? So after that, moving on to the next topic, that is basic components of a computer. So if you want to identify something as a computer, basically there should be some components, right? So they are CPU, main memory, I/O and a connection between them. These are the basic parts of any computer. And simply, even if you consider the computer, although it does several things, even data analysis, data input, like even it is doing multiple of things, but we think, just a moment, it has a possibility of performing the following functions only: the data storage, data processing, data movement, and data control. So to achieve all these functionalities, to achieve all these four functionalities, right? The computers are organized into different structural components. So basically, we have a central processing unit to process your data. You have an input output device to input your data and output your information, and to store them. And you need something like a temporary storage or whatever to working condition, you need a main memory. And in addition to these three basic structural components, there is something called a system interconnection, which glue all these three together, right? As a glue, as a gum, it fits all these three together. That is called as system, the basic components of computer. So this is the overall functional view of any computer. You can control them. There is data movement, data storage, and data processing. So all those functionalities are achieved by the structural components of a computer. So coming from the first one, the first functional unit of a computer is the CPU. CPU stands for Central Processing Unit. It is actually the brain of any computer. It is the one which process how the data is done, processed, everything is done by this unit. That is why it is called as, it is a core of a computer. That is why it is called as Central Processing Unit. Overall, the operations, the data processing, all the functionalities are done by CPU, right? And you know, earlier there was only one processor because our computational necessity was quite few during those days. So they were having only one processor for a one computer. But nowadays, with the growing demand of the computational complexity, we even use multiple processors. Right. So now, as we see, CPU is one major component of a computer, and that CPU itself can be classified into four different functional units. So basically, it has a control unit. Another one is called as arithmetic and logical unit. Third one is called as registers. And fourth one is called as CPU interconnection. Right? So these are the four major components in any CPU. So as you can read from here, control unit means it is the overall boss. So who controls the operation of the CPU? That unit is called as control unit. And in addition, there is one more unit that is called as arithmetic and logical unit. So as the name suggests, it is the one which is responsible to perform arithmetic functions as well as logical functions. So I think you learned in the Boolean logic, arithmetic mean our basic additions like 0 plus 1, right? Or else if you take 1 plus 1, that is arithmetic mean the answer will be what? 1, 0. But if it is a logical addition, we have it like 1. So it performs both arithmetic component and the logical component. Logical part is done by arithmetic and logic unit. All the data processing functionalities of both arithmetic and logical function is done by this unit ALU. So we have another component in the CPU that is called as register. Simply, it is the one which provides some internal storage to a CPU in case if you want to hold the instructions or some data or some temporary stuff. It is the register which hold all these things. Give me a minute. Sorry about that. There were some interruptions here. Right. So this is a register. So registers is something like an internal storage device. For example, if you are making calculations and you want to store some data. So before permanently storing them to somewhere, you need some space to hold it temporarily. That is particularly done by these registers. Just like how all those functional units like CPU, internal output device, and memory are sticking together through the use of system interconnection, here also all the CPU components are also interconnected. Then only there will be a communications among them, right? So these are the components of a CPU. So you see there is a computer. So what I have been teaching you so far is if there is a computer, you can see there are some basic functionalities. Whatever it does, data analysis, typing, or whatever it does, basically it has only 4 functions, right? What are they? Are you listening to me?
Yes, miss.
Yeah, what are those? Here, data movement mean data is flowing inside and data is flowing outside. Data processing mean whatever the data flow inside, we try to process them. And the process data is getting stored. And even we get it as an output. And overall, there is a control mechanism. So there is an overall 4 functionalities. To achieve all those functions, we segment our computer to 4 major components. They are CPU, main memory, I/O, and system interconnection. In addition, this particular central processing unit can be seen as several components because just like other part, this is the most important part now. So we see there are 4 major components within that CPU also. That is CU, ALU, registers, and CPU interconnection. So you can see the first one, this one, the control unit. That person is the person who is responsible for generating the control signals. You try to just, you try to have all the control using this control unit. Simply, the control unit is either done by a hardwired control unit. For example, it is, if you check the processor, it is already using the hardwired, all the things are written. If not, there are some microprogram control unit also, right? These are the 2 ways of implementing a control unit. Simply, he is the boss of the boss, right? Control unit, right? If it is a hardwired control unit, simply, if you're using any logic circuits, it will tell you like how the gate should work, how the flip-flop should work. So something like this. All this will be given by the hardwired control unit. If it is a microprogram control unit, simply there will be a set of instructions only. Like this is a kind of a software, and that is a kind of a hardware implementation. These are the 2 ways of organizing our the control unit. Then next is, before learning the other one, I'll just teach you what is the computer architecture, right? So if you can see, computer architecture means, as I told before, you should have an idea how a computer should function, right? How a computer should function. So computer architecture will tell you what are the basic designs, what are the basic concepts, everything should be there. Our present day computer design is based on a very popular architecture, which is known as von Neumann architecture. So he is the person, there was a person called John von Neumann, and he is the person who proposed one architecture for all the computers. So by his name, we call it as a von Neumann architecture. So basically, this von Neumann architecture is following only 3 basic concepts. First one, if it is a data or instruction, no problem, but both are stored in a single read-write memory. For example, if you want to do some addition, it is done in only one step, one complete step only it is done. If anything is missed in the middle, it is not written to the memory. Second one, all these memory, the content of this memory are addressable by location, because if you consider your memory slot as like a bulk of thing, each unit of the memory have a separate address, and you can call all those values. Either it can be a data or it can be an instruction, no problem. Just by telling, okay, bring whatever the stuff available at 1, 2, 3, the location 1, 2, 3 mean, your computer will bring it. So everything is addressable by location. Third one, execution occurs in a sequential fashion unless explicitly modified from one instruction to the next. Even you can see in the, I think you are learning C programming, right? unless you use a for loop or a while loop or whatever, all the instruction, whatever the code you have typed is being executed line by line. Similarly, here also, everything is executed as a sequential fashion from one to the other. And only if you specify for a jump, right, this will happen. So these are the three basic concepts upon which the von Neumann architecture is working. So based on this component of von Neumann architecture, we have these units in a computer, right? Just like whatever we learned before. This is in a broader context, how in a von Neumann architecture, the basic components are again. So one is memory, the other is CPU, ALU, control unit, registers, and I/O devices. So just like the basic components in a computer, if you want to identify the basic components in a computer using a von Neumann architectural concepts, you have the following components. Memory, which will store both the data and the instructions. Both are there. No matter data or instruction, it is not separately stored. Just as a single read-write memory, it is stored. Next one is CPU. This will help you to process any instructions and data. ALU, as I told before, this is the person who performs the arithmetic and logical functions. And control unit means it is the person which directs the execution of instruction. It controls the overall stack. And registers, they are internal storage provider to our computer. And we will learn this detail in the next unit. We will learn this in detail. And I/O devices is the person which helps people to communicate with the outside world. For example, whatever the input I have to give, computer doesn't understand my language, right? But if I try to type something through a keyboard, or if I try to click using my mouse, the input device is one of the interface which will translate to a form that is understandable by a computer and tell, yeah, okay, the person is doing this. And once the data is processed and the computer wants to talk to me, we need a person like a translator in the middle. Why? Because computer's language we don't directly understand. So all these things, we think the input output devices as a kind of a translator in the middle, who translate the human language to the computer and again back again with the computer's language to the human language likewise. Right? So this is the components of von Neumann architecture. Just a moment. So this you can see as a structural diagram of this von Neumann architecture. So this is your CPU, control unit, arithmetic and logic unit, and you have your input devices, output devices, and this memory unit. So these are the structure, right? I'm getting some call for my Viva presentation with first unit, the CPU part we have covered. And from the next class, I will continue from the second, third, and continue, right? So it's a small lecture I thought of finishing, but I'm getting, right? Getting some calls for this one. Okay. So maybe we can continue in the next class, right? If you have any doubt, I think you all have my number. You can drop it to me or even you can email me. Okay. See you all in the next class. And sorry that I had to leave a little early.